support and encouragement and contribution in this study so far. I say thank you, sir. I equally thank Dr. Kamal Hussein, who has persistently encouraging me for in this program to ensure that this degree is completed within a short time. I equally say thank you, sir. I equally thank the examiners who have, in one way or the other, look for time out of no time to embrace this presentation. I equally express my appreciation and thanks to you people. I equally thank the HOD of the department, I equally thank the HOD of the department, Dr. Ablasha, and the past HOD, Dr. Shamsu Kama, for their wonderful effort and support behind us to make sure that we have this program completed within the short time so that we can go back. I equally thank the member of my team, starting from Sapna Makdoum, for our wonderful support and effort, especially during the hard time, and also his encouragement. I equally thank the Taiba Esan, being the only lady, being the lady, and at the same time the dynamical scholar in our group. I equally say my appreciation to her. Then I equally thank every one of you that embraced this presentation. Thank you very much. The topic of my presentation today is boundary-driven flow over a curved surface. This has been supervised by Professor Dr. Salim Asgar. I would like to run through the outlines of this today's presentation. Okay. Now, the outlines goes as following. We first of all talk about the motivation, the introduction. At the same time, we look at the application area, the background and the geometry. We give the basic magnetic equation, modeling the first problem, the second problem. Then we talk about the conclusion and give a future recommendation. At the end of this presentation, we decided to put down the little reference for today's presentation. Now, motivation. We realize so far that in literature, nonlinear boundary-driven flow through quadratic stretching velocity has never been said. This is one of our motivations, and at the same time, we decided to include the electrically conducting fluid to investigate the effect of Lorentz force in order to, through the variable applied magnetic field. Also, we decided to complicate our research with heat transfer phenomenon, and at the same time to add energy transport source such as radiative heat flux, and at the same time surface frictional heating through what ohmic induction. At the same time, we decided to look at the existing flow geometry in 3 diagrams to express the surface itself from the general point of view. Now, first of all, let us talk about the beginning. Boundary layer theory was coined by Ludwig Prandtl in 1904. This theory represents the flow in 2 ways, which is a laminar and a turbulent. But for the laminar, it has all been said so far in the literature, is classified into 2, elastic and inelastic. Inelastic can also be classified as a fixed boundary. For the elastic case, Sakiadis was first to have studied the moving flow over moving boundary surface in 1961, and stretching was considered by Crane in 1970, and he has considered the linear stretching. For the inelastic, Blasius, who happened to be the student of Prandtl in 1904, first of all considered the flow over surface, which is fixed, and this is what today known as a Blasius flow. And the flow over diverging shyness was considered by Falkner-Scan in 1930. So this idea brought us together and decided to streamline our research into boundary-driven, we started to bring down our research into stretching sheet, which we call the boundary-driven. Again, having done that, then we look at two types of stretching. We have a linear and non-linear. What brought about the non-linear is the fact that most of the real-life scenario may not conform with the linear case. This brought the concept of non-linear stretching, which has been classified so far in literature in 3 ways. We have power law, exponential, and quadratic. The power law was first considered by Bank in 1980, and the exponential was considered by Anderson in 1999, while the quadratic stretching was considered by Taka in 1986. Again, we narrowed down our research to quadratic stretching. This brought this concept of this diagram that we have put together. You can see clearly that after Taka, a decade after, Kumaran et al. in their study, they consider the same similarity problem that the Tata have introduced in 1986 in their own problem. And again, a second decade later, 20 years after, Rakitis et al. Also considered the same problem, considered their problem by using the same methodology that Tata have introduced. But in 2011, Kelsen realized that most of the problem they have solved is inconsistent as a result of the fact that 3 components of velocity were generated and only 2 components of velocity was used. So this gives inconsistency in the model and at the same time incomplete solution that does not actually talk about the physical solution of the problem. So Corte decided in 2012 and put together his effort to look at another direction in another flow and consider the same methodology, and he was succeeded in solving the 3 components of velocity. But what happened in 2020? We decided to extend this concept into curved surface. Now the question now is why we are trying to validate our model with the existing one by taking the large radius of curvature. We realize that the problem they are facing is actually generated as a result of incomplete similarity variable that Taka has introduced in 1986. So what we do is that we first of all redefine the inconsistent in similarity variable. Then we generate the model for the flat plate, and at the same time we provide the solution through homotopy analysis method, which we have done in chapter 3 of this thesis. Now we extend this problem down to curved surface and we generate new similarity variable, and again we generate the model and try to solve the problem numerically as a result of the fact that the system of equation we have at hand is highly nonlinear in nature. So the analytic aspect of it may seem unrealistic. Now we have known that stretching has a lot of application in industry, especially in polymer dynamics, which are not limited to polymer and chemical industry, production of plastic film, melting, spinning process, and nuclear fuel slurries and reactant plants. Now we try to present to us some background from curve stretching study. The fact that Sajid et al. Have introduced the linear stretching of curved surface in 2010, but this has not been the first. It has not been the first case on curved surface. But in the context of stretching, Sajid et al. Introduced stretching of curved surface in viscous fluid in 2010, while they consider linear stretching. In 2013, heat transfer analysis of stretching flow over curved surface has been applied in the presence of magnetic field. But here we realize that the magnetic field, they have considered uniform magnetic field, which violate the law of magnetism, because electromagnetic has to be inconsistent with this law that has been produced or proved by the Maxwell. So then in 2015, unsteady viscous flow, MHD flow over permeable curved stretching and shrinking sheet were considered by Pope et al. Although he has considered the MHD in the same direction with Abbas et al. In 2017, flow of viscous fluid along a nonlinear stretching curved surface was considered by the speaker in his master thesis. And the same year, flow of viscous fluid along exponentially stretching curved surface was considered by OKG. And the last two problems has also been supervised by Professor Dr. Salim Asgar. Now, this is our observation. We realize, like I've said, that quadratic stretching of boundary-driven flow is missing in the literature, and we intend to fill this gap. Also, we try to connect it with the existing literature, which is the over flat surface. Then we consider variable magnetic field for accuracy in order to satisfy the law of magnetism, which we call the Gauss law of magnetism, or sinusoidal nature of magnetism. Again, this inconsistency in magnetism affects the surface frictional heating in terms of surface induction, which is generated as a result of ohmic heating, frictional heating, or called Joule heating. So we have surface frictional heating with variable magnetic field. In literature, it has been considered with uniform magnetic field, violates also the law. We will see the effect as time goes on. Modeling of non-Newtonian fluid, we consider linear viscoelastic, which is Maxwell field, and at the same time we consider some other non-Newtonian fluid, which define shear thinning and shear thickening. Now, this brought us back to the geometry, since we are considering orthogonal flow over orthogonal surface, curvilinear surface. So we first of all look at the right hand side in figure 3. This was introduced by Sagi in 2010. We can see that the surface is clearly expressed where the flow passes through the axial direction, which is x, and we have a radial direction as well, where r remains the radius of the curvature. From the engineering point of view, we decided to introduce another diagram by looking at the isometric view of this. This brought us back to the second diagram as we presented here in figure 3. We have the velocity, which shows the direction of the flow. Then we have the magnetic also perpendicular to the direction of the flow. Then we also have the u infinity, which is ambient velocity, and there's no velocity along the vertical direction, which is radial direction. And r still remain the radius of curvature. Now, since we are applying the magnetic field, we decided to go back to fundamental laws, which we must satisfy that this equation has to be satisfied. Otherwise, they will be inconsistent in our modeling. So we consider this equation 1 to 4. We realize that since in our study it has been done in the absence of electric field. In other words, equation 1 is satisfied, where rho represents the density of the material, and c represents the speed of light, and epsilon naught represents the permittivity of the material. Equation 2, which happens to be the fundamental law of magnetism, must be satisfied because we have to do it in consistent with with the geometry. Then equation 3, which is Faraday's law of magnetism, also satisfied because we are talking about in absence of electrical field. Equation 4, which represents the Maxwell and Ampere's law, where Xm represents the magnetic constant, and then the J represents the current density. It's also satisfied as a result of the fact that E is absent, and we also consider our problem in the absence of induced magnetism, which is B, small b goes to 0. We can see using this B as a function of strength of magnetism and induced magnetism over curve system. Then we realize that the B has to be defined in form of what? R. Now, variable applied magnetic field has a lot of application also in industry, especially in medicine, that's in healthcare system, which are not limited to treatment of cancer and also in the treatment of peptic ulcer. It's also in engineering. It also can be found in the sense of aerospace engineering, and also in the production of materials for controlling a pure crystal semiconductor. It also the application also been found in hydromagnetic power plant, in metallurgy, and biometrics.
How you can apply in the cancer, for example? How can you apply it your model?
No. What I'm saying is that variable applied magnetic field has been found to be useful in the application of treatment of cancer.
What is the influence? What will be the main effect of magnetic field when you are treating your the cancer patient?
Because most of the cancer, most of the cell in the cancerous cell, they are tiny particles which cannot be seen. But the only radiation that can actually destroy these cells is by using electromagnetic rays. So this can be generated using electromagnetic field. But in our own problem, we said that in the application of variable magnetic field, it has been found that this variable magnetic field is more efficient in comparison with the uniform magnetic field. Now we go back by modeling the MEG itself. So we consider first in the Lorentz force, which is E plus J cross B, because our problem we define in such a way that electric charge is 0. So we have F is equal to J cross B, and we have already shown that the B has to take function of R. It has to be radially varying magnetic field, which is defined in equation 5. Now equation 6 itself defines the current density, in which the rho represents the conductivity of the materials, and the V take the velocity field, which is a component of the V and U, where V and U are taking the radial and axial direction. Then, like I said, the V is a function of applied magnetic field and at the same time induced magnetic field. We have, though, using equation 5 and 6, we generate equation 7. That is about modeling of magnetic field. Now, for the viscous fluid, for the time constraint, we decided to start from component of strain rate. We are presenting to us the generalized equation for the component of strain rate tensor. Equation 8 to 11, you can see.
And when you are applying the magnetic field, do you somehow take care of the divergence constraint here?
Yes. Yes, that is why we.
And how you guarantee that one delta P should be 0?
Yeah, that's why we said that for linear coordinate, this delta B equals to 0. We have improved it, and that's why we say that uniform magnetic field does not satisfy it as far as we are working on orthogonal coordinate system. But if it is Cartesian coordinate, it is very easy to prove that delta B is equals to 0. However, if it is perpendicular, we must show that this satisfies delta B because it is the fundamental law for magnetism. If it's not satisfied, then our model that we produce will be inconsistent with the physical problem we'll be discussing.
Mm-hmm.
Now, this brought us back to equation 8 to 11. In any geometry that we are applying, if it is Cartesian, orthogonal, cylindrical, or curvilinear, even if it is toroidal coordinate, these 8 to 11 can generate us the component of strain tensor that we can use in modeling any fluid. Now, how it happens is that by the expression of tensor rotation that we have defined below, we can see that in orthogonal curvilinear system, we define H equals to 1 and H2 equals to 1 plus KR, where K take the curvature effect and H3 equals to 1. So we'll be able to put in those H1, H2, H3 together in this equation. We generate equation 12 to 17. And for VJ, VI, VJ, VK represent the U, and the VU, W, and IJK represent the R, Z, and Z direction, R, X, and Z direction. Now, from the above expression, we present the sixth normal and shear stress component, which is equation 18 to 23, which is obtained from this equation. Rho Ig serve as the component of the pressure term, the viscous term, and the last term represent is the one that preserves the continuity, the law of the fundamental law of mass, conservation of mass, rather. Now, in view of the above expression, we are now going. We take the generalized.
Delta is the chronicle delta.
Sir?
Delta is the chronicle delta.
Yes. Now, in view of the above expression, we now we go back to the fundamental equation that is obtained by Navier-Stokes. So that's presented in 25. For us to complete this modeling, then we decide to take the gradient of stress component in equation 24. So taking the substitute 24 into 25 in the absence of body force, also knowing fully that the continuity equation is what retained, which is equation 26, then we have this problem, two-dimensional curvilinear viscous fluid model, and this has been proved by Sajid in the absence of what body force. Now our contribution is to introduce body force in terms of variable applied magnetic field, and at the same time to connect it with heat transfer.
And what type of force this is? This is a drag force something, or how this force F, this body force?
Yeah, it's body force.
How you apply the body force there?
We have shown that in the diagram. It applies, it's acting upward against the perpendicular to the flow. By the time, if the flow is moving, then you can
what is the effect of this body force on the flow?
That's what we're trying to say. The effect was that if you use magnetic field, the effect is either it's reducing the flow or it increases the flow. But in the case of applied magnetic field, it reduces the flow, and we'll see along in our results. So this is the expression 27 and 28 that has been produced by Sajid et al. In 2010 in the absence of this body force. Now we put together MHD, hydromagnetic viscous fluid, heat transfer, and overall curved surface. So this brought us to heat transfer analysis for nonlinear boundary driven flow over a curved stretching sheet with variable magnetic field, which means that all what we have discussed, we put it together to form this problem. Now the geometry for the physical problem is what we have here. In the surface, we realize that the flow actually induces as a result of the velocity of the surface, which is defined to be non-linear in nature. In this case, the non-linear is not power law, it's not exponential, but rather it's quadratic.
So how you define the linear flow? I mean, how you differentiate between the two flows, the linear and non-linear flows?
Yeah, the velocity that take care of that. The UW, that is velocity at the surface, is the velocity that induces the flow. If the B is equals to 0, as we have it here, then it becomes a UW is equals to what? AX, and that is linear in this case. But in combination with the nonlinear and the B term, then we have nonlinear, which is defined in form of what? Quadratic. It is this velocity at the surface that induces the flow in this direction along the axial direction. While the magnetic field that we apply is along vertical direction. And of course, here we consider the temperature in two cases. We have temperature in terms of constant surface temperature, and at the same time we have variable surface temperature. The temperature can be introduced in two ways. It's either the surface is heated or the fluid itself is hot. Now, this brought us back to the expression that we have obtained. Then we modify this equation by inclusion of what? Magnetic field, as we have here. So this expression, the equation 29 is continuity equation, while equation 30 is the u component of velocity in axial direction. Equation 31 is the v component of velocity in vertical direction. For the right hand side, the left hand side represents the convective acceleration, which is equal to the component of pressure term, the viscous term, and applied the.
And why is the negative sign you have used for the magnetic field?
The negative side, this negative occur in the modeling. By the time we take the,
there should be a reason. Why?
Yeah, the reason is that
positive?
It's there as positive but during the modeling, by the time we are taking the call, we are taking the matrix, then we have negative. Just negative is there.
And if it is when it is negative and when it is positive, what will be the difference?
It cannot be positive, or if it is negative, it will reduce the flow. Because if it is, if it cannot be positive in the sense, that's what I'm telling you. In the sense that while we are trying to model, we pass through, like we shown above, that we have del cross B. That del cross B, by the time we take the chord, what do you call it, transformation, then the negative appear, which means that it cannot be positive. So, like we said.
And this is a sinkhole.
This is a sinkhole. Actually, this is a sink. It could be a source or it could be a sink.
Okay.
This is a sinkhole.
Thank you, sir.
Of course.
Okay. So we have equation 31 to be the v component of velocity. Again, we modify the equation that introduced by Abbas in 2012 with variable magnetic field. Why? The variable magnetic field affected the surface frictional heating because it's a result of what? Magnetic field. They have considered the uniform magnetic field, and we said that the uniform magnetic field violates the fundamental law. So in this case, we modify it by introducing variable magnetic field.
And now you see here it has become positive.
No. If you take this.
Yeah, but there is another sign inside.
Then the typing should be error. It's not positive. Maybe in time, if you are taking the what do you call it? There is error.
You think this should be a positive?
No. It's for the this is for the heat. It is positive because it's different. For the momentum equation, we are talking of applied magnetic field. But for the energy equation, it's different. We are talking about surface frictional heating in terms of ohmic law. So it's positive.
Yeah, but then here this means that the energy is generated here.
Yes. So you will see. We will see along in our result that there is quantum what do you call it? Quantum heat generated by the application of the effect of a Lorentz force that transfers from the surface to the fluid. Now, by the application of a Rosland approximation, we decided to express the temperature, the heat flux in 33. Then we use Taylor series expansion to expand our temperature, and we have 34. Using 34 in 33, and we obtain a 35. By putting this 35 in the expansion and in the expression above for the energy equation, we have the complete model for our complete system for our model. Now, the boundary condition is given in velocity and surface temperature, which consists of constant surface temperature and surface variable temperature. In this case, like we said that the velocity we consider the nonlinear term, which is A and B, represent the strength of the nonlinear. The A is the linear and the B is nonlinear term. Again, because we said that earlier in the literature they have used only the linear term, so we see the effect as we move on in our result. Now, the equation 39 represents the temperature, precise surface temperature, while the equation 38 represents the constant surface temperature, where A and B is defined on a real line. So L represents the characteristic length of the surface. Now, for us to have the boundary layer equation, we decided to. For us to have boundary layer equation, we know. Sir?
It's a bad network quality. Wait.
For us to have boundary layer equation, we try to non-dimensionalize the process and by defining the dimensionless variable as we have in equation 40 to 42. Now, using equation 40 to 42 in the above expression, we have a system of equation for the boundary value for the boundary layer equation. 43 represent the continuous equation, and 44 represent the u component of velocity, and 45 balances the two forces that we have along the curved surface. Because when there is a movement along the curved surface, then two forces must be generated, centripetal force and centrifugal force. But in terms of the flow, we have centripetal force balancing, centrifugal force rather, balancing the pressure force in equation 45. While equation 46 is the complete, after applying the Rosland approximation, we generate 46 for the energy equation. Now we go back looking at to solve this problem, we look at the usual system of solution by defining similarity variable. So one of the novel for this work is that we introduce new similarity system, which is 47, 48, and 49, where M represents the Hartmann number. Now, using this similarity variable in the above expression, which is boundary layer equation, we transform this system into ODEs, which we have 50, 51, 52, and 53. Now, in 51 is obtained from the vertical component of velocity, while 52 represents the u component of velocity. Like we have said that it balances the pressure force and the centrifugal force. Now, in equation 52 and 53 define the two surface temperature that we include in our problem. The RD represents the radiation parameter, EC the cut number, and the PR parental number, and tau represents the ohmic effect, where N is the power index for the precise surface variable temperature. If N equals to 0, equation 53 automatically becomes what? 52. So in this place, we try to look at what is the significant effect of these two temperature in the flow. Now, analysis of the pressure from equation 50 and 51, we generate the pressure term, which is P1, P2, and P3. Now, another novelty for this work is that we're able to look at the total pressure in this boundary layer region as we are provided in equation 57. Now, this takes us back to validate our model with the existing ones. So what we do is that we take the large radius of curvature to be what? Infinity. Infinity does not mean that it must be infinity. You know, of course, we must give a large value so that we have a system of equation for the flat plate. Then we can now compare our model with the existing ones. So after doing that, we generate equation 58 to 60. Now, this took us again back to the fundamental papers on quadratic stretching. So we realized that what they have used similarity transformation that have considered only the linear term without the non-linear term. These do not satisfy the thesis at the boundary. So we redefine that and we generate this model. So we generate this model and we realize that the F triple prime in equation 59 is missing, and G triple prime in equation 56 is also missing. So these are our contributions so far. Although equation 58 has been solved by Suva and Mesha in 31. So we also introduced the new solution for G, because the solution for the G has always been the problem ever since the quadratic stretching has been introduced. So we now obtain a consistent solution for G by using the homotopy analysis method. Now, in order to avoid the time constraint, so we decided to eliminate the pressure from the pressure equation we have in equation 54 to 56, and we have this system of equation for the velocity. Now, it becomes how to solve this. We realize that it's non-linear in nature, which may not be amenable to physical analytic solution. So we decide to apply this. We decide to apply the solution from computational angle. Now, solution procedure. What we do is that since we have three systems of equation and we have two unknown, mathematically it shows that we will have an infinite many number of solutions. So what we do is that we reduce this system into two, where 61 retain equation 61, then equation 62 and 63 reduce to what? Equation 64. So we solve equation 61 and 64 along with this boundary condition, dimensionless boundary condition for both velocity and heat. Now, this is our numerical computation, the algorithm that we have used. Firstly, we initialize the boundary value problem into initial value problem by using this variable. And again, we approximate the boundary condition, the missing boundary condition that we have. We approximate them with Taylor series, using Taylor series expansion to expand that. And we use the Taylor series expansion also to construct Newton-Raphson algorithm, which take care of the convergence region. At the same time, it's also take care of the shooting method. So the unknown initial condition set to be W1 to W6, and in the default initial condition, the ODE file return the primary information, which is time span, initial condition, and the options. The option take care of the errors at which our solution is valid. So today's presentation, our solution is valid at the tolerance of 10 raised to the minus 8. And shooting technique is set up to handle the equation simultaneous with what? Longitudinal fourth order using MATLAB command fsolver and at the same time ODE 45. The solver repeatedly called the ODE file to compute the set ODE at various times. So the control statement produces the type of output required so that the ODE file can pass the pertinent information to the solver. In the Jacobian case, the MATLAB ODE 45 return the file. If Jacobian matrix gives us infinity, it shows that our initial guess is far away from the solution. So we need to supply another initial guess so that we can be close to the solution and it will be able to compute the solution accurately within that error that we have specified, 10 raised to the minus 8. So once all the initial conditions are obtained, automatically the solver displays the required plot and the numerical value in the command window, and the computation is what terminated. Then this now leads us to result and graphical analysis. Now for the graphical analysis for the solution for the problem, we realize that we have the F and G. The F and G represent the stream function. We actually define or expresses the flow trajectories of the fluid along the curved surface. So what happens is that when we enlarge the dimensionless radius of curvature, the surface tends to what? Flat, and the velocity decreases. In other words, we are saying that by the time we shrink or we reduce the dimensional radius of curvature, then the flow will be what? Enhanced. It means that the streamlines flow faster in over curved surface as compared to what? Flat surface. And we should not forget that the G represents the nonlinear part of the system. This is most significant of this study because it contributes significantly. So the quantity you can see there, the contribution from 0 to 0.3. Even if you add it to 0.3 to 1, it's even greater than 1. So this is a significant effect that we cannot neglect it. In the previous paper, the G has been always been neglected, which affects their solution, and we say that the solution does not represent the physical solution of the system. So this is the effect of dimensional radius of curvature on stream functions.
So how you choose the value of this xi, this parameter 5, 10, 20 and 1000 like this?
It's a numerical computation. We randomly choose some in some articles.
Some random value or based on some geometry or physics?
Like I said, the physics was that if the surface tends to infinity, we must have this dimension radius of curvature to be large.
I'm just looking at the variation from 5 to 10 and then from 10 to 20 and then from 20 to 1000. But the variation in the graph
is
very much.
Yeah, it's very good. It means the reason is that in the system, the reason is that if you extend the dimensional radius of curvature, the flow reduces along with it. So at the time, the effect will be insignificant. That's actually what is displaying. Then, if now turn to curve, then the the effect is more significant in the curved surface. So actually, the value has been taken randomly, like we say it is a numerical. In some articles, they have used a lesser value, but we realize that if you use 0.1 and 0.2, may not actually represent the physical meaning of the system, because 0.1, by virtue of what they call it, geometry, it will very thin, and that will not actually represent the flow system physically. So we decided to enlarge this further by taking 5, 10, and to 1000.
And 10,000, for example.
At 10,000, there's no effect anymore.
Almost.
The reason is that even if if there is a flow along the surface, Okay, a time will come, by the time you raise your hand, you are touching the flow. A time will come, you will not touch it. At that point that you are not touching the flow is the infinity. Okay. It's not necessary that it has to be higher value. So when you take 10,000, 1 million, the effect will not be, it will be insignificant to be the same. So this represent shows that the flow trajectory reduces and over the surface and increases via a curved surface. Now this is consistent with the velocity, as we can see that enlarges the radius of curvature, reduces the velocity, invariably shows that the flow increases over curved surface and at the same time expand the momentum boundary layer. But here it shows that it reduces over flat surface and shrink the momentum boundary layer. While figure 6b represents the effect of applied magnetic field that we have considered variable magnetic field. Increasing this parameter increases the Lorentz force, and Lorentz force opposes the motion. Therefore, the velocity reduces. Even if it's over flat plate or curved surface, the velocity reduces. So that's what we have seen in equation 6b. In figure 6b. But the graph that we are presenting over is not what matters most in this study. What matters most is figure 6c and 6d. Is our concern the effect of the linear and the non-linear term itself on the velocity. We can see that simultaneously in figure 6c and 6d, the velocity increases and also the momentum boundary layer increases. So what happens is that what is the significance or what is the contribution of this non-linear term that we have claimed that the previous study have neglected? We realize that it plays a vital role. It plays a vital role. You can see clearly that it increases more than the linear term, and this can be justified by plotting the pressure term as we have in figure 7. Figure 7D actually show the contribution of B. You can see the pressure rises faster compared to the linear term. So combination of this enhances the flow compared to the linear and section sheet. Now, analysis of the heat flow, temperature. The increase in by the time we increase the Prandtl number, we realize that the temperature decreases. This is the consequences of what? Decreasing the thermal conductivity of the fluid. This shows that for us to increase the temperature, we have to actually reduce the Prandtl number. So we plot this in two cases for the CST and the PST. So we can see clearly that for the CST, the temperature is more, the thermal boundary layer expand more than the PST case. And for the figure 8b, we see the effect of Eckert number. Increase Eckert number actually expand the thermal boundary layer. The reason is that the viscous dissipation generates more heat and actually increase the velocity and at the same time contribute to enhance the temperature and as well as thermal boundary layer, thermal boundary region. You can see. But in these two graphs, you can see that the case is more severe in CST compared to PST. So which means that physically, PST can be used to reduce the temperature in the system, and the constant surface temperature can be used to maintain this temperature in the system. In all the figures, like we have in figures 9C and figure 9C is the effect of radiation. Increasing radiation number actually enhances the temperature and at the same time enhances the thermal boundary layer as well. And while in figure 9D, you can see that if n equals to 0, like I said in our model, that the equation PST gives what? The CST. So that shows the line, the blue line. N equals to 0, it corresponds. It maintains the temperature in the system. So for us to further reduce the temperature or to decrease the temperature, we can expand the values of n, which means that prescribed surface temperature can be used to reduce the system temperature and at the same time shrink the thermal boundary layer in the flow. And this is the contribution of surface frictional heating by ohmic induction. You can see increase the parameter from 0 to 1.5. We can see the effect 1 to 1.2. It contributes significant. That shows the quantity of the heat transferred from the surface to the flow, from the curved surface to the flow. And of course, the same effect also seen that the PST reduces compared to what? CST. And figure 9F shows the effect of the Lorentz force. Like I said, it generates the quantum effect of heat, which transfer from contribute to raise the temperature in the fluid, as we see there. So In scenario, we realize that the PhD case can be used to reduce the temperature in the system, while the CST can be used to maintain the temperature in the system. That is what the comparison is all about. Now, physical quantity. In question 69, 67, we have generated to produce the surface drag force and then numerical Nusselt number, which is a rate of heat transfer. This, we use it to validate our model, to compare our model with the existing one. We realized there are differences in the result. In our past method, they have used uniform magnetic field. Like we said, it violates the fundamental law of magnetism, and why the present result have considered the variable magnetic field, which satisfy this fundamental law of magnetism. So that's why we are seeing slight variation. Now, for the second problem,
so I have one question. Okay, what was the computational time for calculating one result, for example? One question, and the second is, because there is a Jacobian matrix involved in your calculation, is there any parameter values for which your code fail or your result you cannot generate?
Yes. Yeah. Sometimes if we increase parameter beyond a certain point, the Jacobian will fail. In this problem, when we decrease it, because we are using we are using the shooting method. If I decrease the dimensional radius of curvature like let's say 0.1 and 0.2, the Jacobian will be infinity, it will fail, it will not compute. So I will increase it to have a result. Although I have set the error, the convergence to be within the error.
Have you mentioned this in your thesis that for this case your Jacobian matrix will be singular, for example, and then you will have no result, and then this model may not work?
No.
Yeah, because when you generalize something, then it's very important that you should also point some then where your result are not generated or your code failed.
Okay.
Maybe in future.
All right, sir.
Yeah.
Thank you, sir. So for the second problem, for us to have for time limitation, we decided to present the model straight away without looking at the modeling itself. So it consists of linear viscoelastic fluid, which is Maxwell fluid, along with the MHD transfer and curve surface. So this brought us to thermal analysis of hydromagnetic viscoelastic flow over a continuous curve stretching sheet in the presence of radioactive heat flux. And again, we present this in this geometry. The difference is that for the first case, we consider nonlinear stretching velocity. In this case, we consider the linear case, where n represents the strength of the linear stretching. And here we consider the radiative heat flux, which is generated from the Fourier's law. So we have the R also retain the same radius of curvature and B along vertical direction. So this is the geometry for the problem. So the governing equation remains from 71 to 74. The 71 in continuity as we have it above. The difference is that here we have the time. We have the time effect, which shows with the lambda. That gives the constant time of the materials at which the deformation occurs, the elastic behavior of the fluid. That take care of the elastic behavior of the fluid. So we also have the viscous term, the pressure term, and the body force. So we have the U component velocity, V component velocity, and the energy equation. The energy equation remains the same. Consider the viscous dissipation at the same time. Consider the surface frictional heating along with ohmic heating. So the bounding condition for this case, we consider the velocity, like we said, the linear velocity, and we consider the temperature in twofold: prescribed surface temperature and the prescribed surface heat flux. So we define from 71 to 77. Now again, to look at the boundary layer equation, we also take the non-dimensional process by defining the dimensional variable from 78 to 78 and 79. Introducing that in the governing equation, we realized the boundary layer equation to be in this form, like we have said. So A take care of the constant time of the elastic behavior, and we have the viscous and the the body force. And 82, equation 82 retain the same way. The balances the force, the pressure force, and at the same time centrifugal force. So by virtue of Rossler approximation that we have discussed above, we introduce it in the energy equation, and we have the system completed. So solution concept, we define the similarity variables in this direction, in this form. and we have m to the what? Hartmann number. So we transform this equation again into ODE to have 88 to 90. The 88, like we said, balances the pressure and the centrifugal force. The 88 generated from U component velocity and the energy equation given 90. So we eliminate pressure from 88 and 89 to have equation 91. So it becomes a challenge to solve equation 91 and 90, the energy equation and the velocity equation, along with this boundary condition we define 92, 93 and 94. 93 take care of the prescribed surface temperature, dimensionless prescribed surface temperature, and 94 take care of the boundary condition for the prescribed surface heat flux. So we solve the same again with
how
same.
you choose these initial condition? This is some link
Yeah,
with
like
the geometry.
yeah,
Go back to
the initial condition,
condition.
like I said in the geometry. Like I said in the geometry, this initial condition is obtained from Fourier's law.
Okay.
You can see. While the second one is just constant surface temperature. Yeah.
Okay. So the initial condition in your model.
Yeah. So when we transform it, then we have this 93 and 94 for the energy case, two case. Now.
This is boundary condition. Initial condition.
Yes.
Yeah.
No, initial condition.
Okay.
Because we have transformed to ODEs. So we have numerical computation the same way. We use the same method along with what RP4. So then we present our result. We decided not to present velocity case because it's the same way. The effect is the same way as we have discussed above. The effect of curvature on the velocity, it reduces over the flat surface and it increases over curved surface. So here we decided to look at the effect over the temperature, the two cases of temperature. For the first case, we have increasing dimensional ranges of curvature shows that the temperature reduces and the thermal boundary layer shrinks. And the two cases is observed. In these two cases, the same is observed. But the significant effect is that in this we see the quantity of heat contributed by this curvature is what this is showing, because this is a heat flux. It's not showing that the total heat in the system, it's showing the quantity of the heat contributed by the curvature to the fluid. We can see in another result what I'm trying to talk about. But for the 11B and 11D, if you compare of a magnetic field, we realize that increasing the magnetic field actually increases the Lorentz force, and increase the Lorentz force actually increases the temperature.
So you are looking on the effect of different parameters on the temperature profile, yeah?
Yes.
But I see that these effects are very minute, very small change, a very small effect, yeah. And it is also in a certain region. In otherwise they are the same. So
no, it's not the same. Here is 0 point. You can see there is variation. For the first one is from 0 to 1, while from here is 0 to 6. What we are trying to say is that for the second case, which is precise heat flux, it shows the quantity of.
No, but the curves are very closer. I mean, there is very little minute effect.
Yeah. But it increases.
Can you? Yeah, it is increasing, but it's not much. So can you explain why this the changes are not so drastic? You can say. And
the reason is that the quantity of heat generated as a result of the Lorentz force is not that much, because we are not increasing the magnetic field. You see the difference of our increase 0.0.
And how we can amplify or increase what I have to do in order to increase these effects? Or you can say they magnify these effects or enlarge these effects.
Okay.
What could be done, you think?
Yeah.
What is your conclusion?
We can actually increase the what do you call it, the parameter itself. We can actually increase the parameter itself.
Have you checked it that if you change these and then you see a more difference between the profiles?
Yes, because if you look at it, the difference here is different from the difference we have in the precise surface temperature.
But
the two are different. The effects are different.
Not much.
Not much, but they are different. The difference are. Sorry.
And they have the same initial condition for both?
No. This is precise surface heat flux, while this one is precise surface temperature. So there are two differences. This one is generated from the Fourier's law, while this is just the constant temperature at the wall when the surface is heated.
So what is the initial condition in your third graph and fourth one? Because it seems that there is
This one?
Yeah, initial condition for this. Because this is the initial value problem. So
Yeah.
what is pi of 0 is equal to what?
Is 0 to 1. Well, that's why I explained that this is showing the quantity of the heat contributed by the conversion effect.
Okay. And
Yeah,
that-
well, this one is showing the quantity of the heat generated by the Lorentz force contribute to the fluid itself.
So what was your initial condition in your model?
0 to 1. That's what 0 to.
So you have dimensionalized actually.
Yeah, we are not. I've explained that we don't dimensionalize.
Non-dimensionalized.
Yes.
Yeah, and that's why you have put it between 0 and 1.
Yes.
Okay.
Okay, go.
Now, temperature profile, we realize by the time you increase the Prandtl number, also the same effect is seen as we have explained above. It decreases the thermal temperature in the region and also shrinks the thermal boundary layer. But when you compare the two temperature surface, one, you realize that when you compare these two graphs, you now realize that it enhances here from 0 to 2.5 and above. The reason is that this is actually showing the total temperature in the system, meaning that the prescribed surface temperature, prescribed surface heat flux can be used to enhance the temperature in the system, while the prescribed surface temperature can be used to maintain the temperature in the system. So when we decrease the Prandtl number, then we can increase our temperature in this part. On both cases, we can increase the temperature, but the effect is more significant in the prescribed heat flux as compared to prescribed surface temperature. And this equation figure 12a and 12b is plotted for the viscous dissipation, in which the Eckert number represents the effect. When you increase the Eckert number, like I said, it enhances the temperature in this flow and shrink and expand the thermal boundary layer. But here the effect is also significant, meaning that it shows the total temperature in the system as compared to as we have in conversion. You can see that it reduces here. So this is a quantity of the heat generated from the surface to heat. Now radiation on both sides, radiation being the additional source of heat. So radiation being the additional source of heat is also increase the temperature and expand the thermal boundary layer. And at the same time, we also see the contribution of surface frictional heating. This one is showing the quantity of the heat generated as a result of the Lorentz force from the surface to the fluid. Now, physical quantity, we see variation of surface drag force and Nusselt number, which we plot as a result of equation we generated from 95, 96, 97, and 98. Then we compare our results. We see the surface drag force and the rate of heat transfer we compare with the bar setup. So we realize that there are differences, like I said in the previous slide, that the difference is due to the uniform magnetic field and the variable magnetic field. So when you look at it and we show the error that has been occurred, the error is due to the uniform magnetic field and the variable magnetic field, and this is justified the reason. When you go down the table at 1000, where we assume that the surface is now flat, you realize that the error is decreasing, is going gradually. So meaning uniform magnetic satisfy the geometry they have used, and for the curved surface it does not satisfy.
But
Because
0.01 and 0.009 is not much difference again.
Sir?
0.009 and 0.01 is not so far from each other.
It's far, 0.1 and 0.009. It's in terms of engineering, from engineering point of view, it's far, because by the time you have a minute, a minute system, then 0.9 will have.
I would like to see what is the next digit after 9.
Sir?
Well, I would like what will be the next digit after 9.
The next digit after 9. Okay, 0.1.
But you know, in exile there is a huge difference from 200 to 1000.
Yeah.
1000, yeah.
From 200.
200 to 1000.
You know, I've told you that
Yes.
I've explained that as we go over the surface, the effect seems to be very minor.
Okay, man.
Now, in conclusion, we have presented the heat flow and we have discussed it in two cases: constant surface temperature and precise surface variable temperature. And we also consider the precise surface temperature and precise variable heat flux. Then we also correct the modeling in flat surface, and at the same time we generate the correct accurate model for the curved surface, and through quadratic stretching velocity. We also discuss the variable magnetic field in curvilinear geometry. Otherwise, the model will not be the model will be inconsistent. And we also discuss the effect of the linear and non-linear part of the stretching velocity. And we also discuss the significance of heat transport source, such as ohmic heating and radiative flux. Then we also present the geometry from engineering point of view. Instead of us to use the existing geometry, we consider the new geometry by looking at the isomeric view in general. So for future recommendation, the result we obtain for non-linear quadratic stretching can be used now in any model. In any model, you can extend this result: cylindrical, polar, curvilinear, toroidal, and also what you can use this result for any model. Then the modeling that we have done for the linear viscoelastic, which is Maxwell, can also be extended in many directions. And more research work can be generated from the modeling of non-Newtonian fluid that we have discussed, which we have in our thesis, cross fluid and the suitable fluid. Then also the unsteady flow cases of this present work, they are front line of another research which actually some scholars may decide to look into. So these are the references for our presentation. Thanks for your attention.